So we are continuing with known relativistic force orders. So in that sense, we have been seeing Dirac equation, uske the solutions, and how we just took the answers. Answers means हमने वो once we modified the second order differential to this, तो we assume that it should have this form. ठीक है, इक्वेशन को हम मॉडिफाई करके, बट उसकी एक्सप्लेनेशन हमारे पास नहीं थी. So at the end, what we are going to motivate it, the sort of assumptions we are starting with, whether it's a second, how we can do it with the negative probabilities. तो हमने उसका एक फॉर्म दिया था, derivation का फॉर्म दिया था. It was like this. We did not exactly justify it. C by lambda. Plus beta MC square is equal to x side. Alpha 1, alpha, they are different matrices may correspond. So assuming this, we just did the previous thing. Now we are going to see, we can say this equation can reduce to, for a particle at rest, means you can ignore these higher order terms. For the simplest case, this equation may be written as, for the particle, see goes to 0, you can ignore these first three terms, so you can write it like this. Is basically and since your de Broglie wavelength हमारी है, it's very large and it exists for all spaces, तो अब ये है कि हम we are going to for a particular value of this beta, in some sense, there can be four solutions. Solutions ऐसे आएंगे, psi 1. Solutions basically आएंगे ऐसे, basically है ना, E is equal to E square is equal to MC naught square C square, it will be plus minus. So it can be, the solutions can be like, if you assume the solutions of this can be, so अगर हमारे पास ये 4x4 matrices हैं, ठीक है, तो क्या आएगा, तो इसकी the form, in the column form, it can be, अगर इसका solution आएगा ऐसे आ सकता है, 1 0 0 0. psi 2 का आएगा ऐसे, minus iota MC square by h. Now 0 1. Psi theta, you can take it as 0 0 1 0. Psi 4 will be 0 0 0 1. So you can have this 1 0, so you can see it here. Up here it's 1 0 0 0 0 1 0 0. So they will correspond to different. So अब इसमें भी दो solutions हमारे पास है ना. We are going to plus minus plus minus. So we will only not take the negative solution. Negative solution में हमारे पास क्या है? For example, Hamiltonian जो है, it's P square C square plus M square C4. So we are going to suspend. फिलहाल हम इसको suspend करेंगे. इसमें जो negative energy solutions आएंगे ना, they will correspond to anticoactions. They will correspond to and their logic. We are going to इसका logic जो है ना for negative solutions. We are going to pin down. फिलहाल the aim of our class is whether this sort of equation which we have introduced इसकी validity बनती है कि नहीं. So we are going to check its solutions in some specific way. So if at the end it gives some experimental or empirical results which agrees with the experiments, so हम कहेंगे कि we have assumed something, it's fine. Okay, this is the way it's working. Apart from the fact, we are going to postpone this thing whether we have particles or antiparticles. Antiparticles, the negative energy solutions को हम फिलहाल we are not going to concentrate on that. So in an external, for example, so we can introduce two component poly spin cable, where this electromagnetic potential can be written as, so we can write electromagnetic potential in terms of phi's and a's. एक तो है ना इलेक्ट्रिक फील्ड कैसे आप रिप्रेजेंट करते हैं in terms of phi, del phi, but in electromagnetic we also have a dA by dt also, है ना. So if we have a in this form and जो इसका gauge invariant substitution, so accordingly जो momentum है p mu, it can also be modified as a mu. Okay, our definition of momentum in presence of these gauges. ठीक है, इसमें phi भी है, a भी है. So in that thing we can, and जो हमारे पास momentum है, for example in class it can be written as this is p. It can be 0, 1, 2, 3. 0 is time derivative and other is speed. Now we can say, so if I'll just so these are different numberings in the equation. Maybe if this is 1.130 and 42. So if we just see it this way and substituting 1.5. So, अगर हमारे पास हैमिल्टोनियन है, हैमिल्टोनियन if you remember it's iota dh by dt, and जो हमारे पास श्रोडिंगर इक्वेशन की फॉर्म है, it's basically h square del square by 2n psi dt. So if it's 1.5 and 2.5. 1.25. हाँ, so अगर हमारे पास एक तो ये सब्स्टिट्यूशन है and this substitution, so we are going to substitute it in this. So our how we have defined Hamiltonian like this, and how we have under redefinitions of gauge के हिसाब से momentum को हमने redefine किया in terms of A's also. इनको हम substitute करेंगे in our original equation. So the equation will take this form. Equation बोल सकते इसमें आपको we are going to rearrange these things in some way. So it will be like this. This is equal to C alpha. C alpha means you can include alpha 1, alpha 2, alpha 3. There are different matrices here. C alpha. And this जो हैमिल्टोनियन है हमारे पास, so no sorry, maybe it's at C. So it's C alpha dot of this P mu minus E by C into A mu और A0 के लिए हम कर सकते हैं A plus beta MC square plus E5 sin. Yeah, it's like this. This is iota H D side. अब ये जो इक्वेशन है ना बेसिकली व्हाट इज इट रिप्रेजेंट? इट रिप्रेजेंट्स फॉर एग्जांपल मिनिमम इंटरेक्शन of Dirac particle which is assumed to be a point particle, ठीक है? Point particle applied in शाबाश कहाँ पर अप्लाई करते हैं? In the electromagnetic field, applied electromagnetic field. इसमें गेज पोटेंशियल ए बी है एंड फाई भी है ना, ए बी है एंड फाई भी. नॉर्मली ई इज इक्वल टू डेल फाई माइनस डी ए बाई डी टी, ऐसे करते हैं ना. एंड बी इज इक्वल टू you can have phi is also there and A is also there, okay? So you can have the interaction of free Dirac particle in terms of electromagnetic. उसकी equation हमारे पास it's like this. अब हमारे पास करेंगे काम इसका क्लासिकल पैरेलल. क्लासिकल पैरेलल में क्या करते हैं? हम कोई भी हैमिल्टोनियन लेते हैं H plus H naught perturbed along some मिनिमम लेते हैं ना, जिस तरह आप वो हैमिल्टन जैकोबी इक्वेशन किए ना, या व्हाट वी डू समथिंग लैग्रांज या हैमिल्टन वी परटर्ब बिट इंटीग्रेट करेंगे, इट विल गेट द इक्वेशन ऑफ मोशंस बैक, है ना, परटर्बिंग अलोंग सम मिनिमम, देन यू कैन इंटीग्रेट इट इन बैक. These are the set of this matrix. C alpha may be a sort of operator in that sense. And in this case, we take a particular operator which is called velocity operator. In the classical expression, such that the interaction जो point at classical maybe E by C, इसको हमने ये velocity operator लिया, we can also write it like this. So classical Hamiltonian का form for this Dirac particle, it's like this. That sense. And we have introduced V as here as a parameter. अब हमारे पास, if you remember, जिस तरह आप क्लासिकल मैकेनिक्स में पढ़ते हैं ना, पॉइसन ब्रैकेट है ना, उसकी फॉर्म क्या है in terms of commuted. And once we make classical quantum analog in terms of Poisson brackets, वहाँ करते हैं ना, हम कैसे करते हैं? Earnfest थ्योरम करते हैं ना. How we can जो classical variables, classical mechanical variables, how they can be related with the quantum mechanical variables. हम क्या कहते हैं? At for some suitable limits, classical variables is theorem particularly also. The quantum mechanical variables can be treated as classical variables. या classical mechanics, जिस तरह आप कहते हैं lambda is equal to h over simple argument and for very heavier masses. We say de Broglie wavelength is too small. So we can say for lower scale structures, classical mechanics holds. है ना, ये simple argument है from this. In the same way, Earnfest theorem may be the argument of how we can relate classical variables with the quantum mechanical variable via Poisson bracket formalism. This language. तो वहाँ पर commutator zero नहीं आता है. Commutator iota by h आता है ना, plus some. हाँ, so वो जो वो argumentation है वो वहाँ से लेते हैं. We are going to use here that argumentation as a relativistic extension of Ernst relation where d by dt of r. So I just recommend you. So it means another thing. So it's an exercise at the end in the book. How we arrived at it. Here I am not going to show you. Okay, it's just an exercise of okay. How so can we write them like this? The last one you can understand. It's a QE plus QB cross B. है ना? ये ना charge. F is क्योंकि particle है ना under electromagnetic field. In electromagnetic field F is equal where जो pi हमारे पास है pi, this pi can be written as p minus. So you can say in simplest cases हम जो using Poisson bracket formalism, how can जो हमारी redefinition of Dirac equation है in presence of element phi, उसका form ये है. And for free particle इसका फॉर्म अगर ये है एंड अगर हैमिल्टोनियन को हम स्लाइटली परटर्ब करेंगे इन द सम सेंस, सो हाउ कैन द इक्वेशंस का फॉर्म ये आएगा. वेयर यू नो इन योर स्टडी ऑफ इलेक्ट्रोमैग्नेटिक थ्योरी, जो हमारे पास E है, E का फॉर्म क्या है? Del phi, and B का फॉर्म क्या है शबद? Del cross. Now again what we are going to do is we are going to take इससे पहले जो हमारे पास इक्वेशन थी ना, ये आयोटा एच साइड यू कैन सी जो जिस पे हम ये सपोर्ट कर रहे हैं. So we can take so we can इसको इसकी हम higher order terms लेंगे, higher order couplings. फिलहाल we are just taking only first few orders of couplings, which will explain for us the spin of the electron. And उसके भी दो orientations हैं, ठीक है? And उसका magnetic moment. So these can have higher order couplings. We are going to ignore this thing in the फिलहाल के लिए. And फिलहाल we are going to take only इसके जो हमने कहा दो positive solutions, ignoring the negative solutions, which will see later that they correspond to the antiparticles. तो हमारे पास जो होगी equation, so अगर हमारे पास wave function psi है, इसका two component form आएगा ऐसे. Then इसका two component form we can write it as d by dt. ये basically psi है ना, psi. Psi का हम two component form लेंगे, ठीक है? Which will correspond to those positive solutions, ठीक है? So in terms of phi and in terms of chi. So इसको आप लिखेंगे this equation can be written as in terms of this C alpha. C अब ये alpha ये है ना, we have done यहाँ पर C alpha in terms of हमने in terms of pi लिखा है. pi को हमने ऐसे लिखा है. And थोड़ा सा इसमें we do some algebra, so you can write it like this. Plus mc square phi of minus square. अब in non-relativistic limit, these equation can take the form in non. So वहाँ पर हमने लिए थे चार मैट्रिसेस e to the minus mc square 1 0 0 0 फिर 0 1 0 0 फिर 1. So we will take positive solution. So in the same way, in terms of phi and chi, we are going to take phi chi e to the power minus. Where phi and chi जो हमारे पास है, phi and chi are slowly varying functions of time. ये है ना यहाँ पर की, they are slowly varying functions of time. So we can now, since T is included here, we can also include, take into consideration kinetic energies, है ना? Kinetic energy क्या है? 1/2 mx dot square, है ना? Okay. So we can say for a small interaction, kinetic energy and field interactions. Energies. We assume kinetic energies and field interaction energies are slower as compared to mc square. Okay. This for lower energies we are taking into consideration. This equation for 4. So just give 5 minutes. Okay, maybe we leave it here, this time, because tomorrow we are coming to the important result after this. So should I take 5 minutes more? Okay.